The aim of DSP Lab Experiment 3 is to measure the heart rate from a PPG signal and identify the pitch frequency from a given voice message. So this is the code for measuring the heart rate of a PPG signal. As we can see, given the offline data, we have stored the data in an array called X, and we have declared another array R for calculating the autocorrelation function. Now we know from that the property of autocorrelation function is that it will have a maxima at origin, and then when it has the next global maxima, we will find the fundamental frequency of the signal. So in this case, because it is an offline data, we have done the calculation within the setup because it needs to be done only once. What have we done during the calculation? First, we initialize the serial communication with the monitor at 9600 baud rate. Next, we find out the autocorrelation function by using the formula sum equals to sum plus x of n into x of n plus m, where n varies from 0 to the size minus m minus 1, and m varies from 0 to 150, that is the size of the original array signal. Next, we normalize the autocorrelation signal by using this method. We start from the right hand side of the array, so that we don't need to use another variable to store the max data. We can use the R0 data itself and initialize and normalize the array, whereas we'll get the origin value as 1. Next, we have normalized the PPG signal as well, so that we can see the two signals together at once in the serial plotter. Otherwise, if they are not in the same range, there will be a gap difference, so the waveform will not look nice. Next, in order to find the frequency, we first find a zero crossing point or a minima. We will find a zero crossing point if the data has been pre-processed. However, if DC drift is present in the data, we won't find a zero crossing point. Therefore, we can also make do by finding a minima. In this case, I have found the minima here through this method Ri less than equal to Ri plus 1 and Ri greater than less than equal to Ri minus 1. That gives us a minima. And once we find the first minima, we can say that we will find the fundamental frequency after that. So we come out of the loop by changing by keeping this checkpoint, is the minima found or not. After the first minima has been found, we theoretically create a window from that point to the end of the array, and we try to find the global maxima there. That has been done here, and as we find the global maxima, we store the index of that point in this variable max I. So that is the point, that is the distance that will give us Lmax1. So from that Lmax1, we know that the sampling here has been done at 50 Hz frequency. So what we do here is, in order to find the bits per second, we divide 60 seconds by the time period. The time period can be found by the index of the maxima, that is max I, divided by the frequency 50 Hz. So in this way we find the BPM. So at this point the calculation has been done, and we just need to print the current beat per minute. So that we do in loop, so that it is done again and again. In this case, we see that we print both the original array as well as the autocorrelation signal that we can see in this plotter. As we can see, the blue data is the PPG data, and the DC drift has been removed. That's why we can see zero crossing points here. And the red data here is the autocorrelation data. We can see that there is a sharp peak at origin, and after that we see the smaller peaks, whereas the distance from the sharp peak to the first global maxima will give us the frequency of the signal. The beats per minute will be printed in the serial monitor. That can be seen also. As we see in this case, the heart rate currently is 63.83. So we can see that it lies within the normal range of human heart rate, that is 60 to 82. So we can assume that the experiment has been done correctly. Now to find the pitch signal of audio signal, pitch frequency of audio signal. The audio was recorded at 8000 Hz frequency, sampling frequency, and for 1 second. The audio was at .wav format, and we have translated that into a .csv file by using Python. Now we consider a frame of 30 milliseconds. That is why we take 240 samples and store that in an array X. Now the exactly similar processing has been done to the array, and thus we find the frequency, the pitch frequency, which is the fundamental frequency of the voice. However, in this case, a small change has to be done, since the sampling rate changes from 50 Hz to 8 kHz, and we are not finding it in terms of per minute, rather per second, that is Hertz. So we substitute the 50 term by 8000 and the 60 term by 1. That is why we find the pitch frequency by doing sampling frequency 8000 by the index of the global maxima other than the origin data. So in this way we can also see the pitch frequency what we find here. For that we need to first upload the code to the board. Okay, there are some minor errors here that we see often due to the architecture of the Arduino Duo board, and according to certain sources this can be fixed by putting a resistor between 2 points that I am not sure currently. However, restarting the board also helps, as we can see here. And an interesting thing to notice here is that although the board Duo is a more advanced board and has more storage, we see the uploading time is quite more as compared to Arduino Uno. Now we see here the pitch frequency that we find at 186.05. As we know, the range of human female pitch frequency is between 180 to 250. So we assume that the speaker in this case was a female, and we conclude that the experiment was done correctly using offline data. Now we can also do a real-time heart rate sensing using a code similar to the experiment 2, where we used a PPG sensor to measure PPG data and find the frequency. So what we do here is, again we use a counter to notice if to determine if we are to process the data or if we are to calculate. So in this case also, because the code has to run again and again, since it is a real-time product, the code will be written in loop, and in setup we have just initialized the sensor input and the serial communication. What we do in the loop, however, is through the counter we first read the data into an array with keeping a delay of 10 seconds so that we match a sampling frequency of 100 Hz, and we keep the counter, we keep inputting the data into the array till the counter reaches 150. So we take the data from the sensor for around 1.5 seconds, and then we do the similar processing as we did in last time. We remove the DC drift, and then we find the autocorrelation function, and then we, from that autocorrelation function, we find the current beats per minute of the signal, and we print that in the serial monitor. Thank you.